Welcome to the deep dive. If you are listening to this, you're probably the type of person who is insanely curious, consistently following the latest tech trends and always wanting to stay ahead of the curve.
Absolutely.
You want to know what is actually happening at the cutting edge, but you just don't have the time to get bogged down parsing through thousands of pages of academic research or dense technical documentation.
Right, because who does?
Exactly. So we do the heavy lifting for you, distilling multiple high-level sources into the most critical insights. And today, we have a really complex and rapidly evolving topic, which is the structural shift toward large language model-based autonomous agents.
Yeah, and the transition we are looking at today really represents a fundamental change in computational architecture.
Mm.
To break this down, we're synthesizing insights from an excerpt of the GenAI Foundation's podcast, which covers state-of-the-art generative AI papers alongside our primary roadmap for today.
Which is massive.
It is. It's a comprehensive 2025 review article titled A Survey on Large Language Model-Based Autonomous Agents. And this was authored by Wang and a huge team of researchers from the Renmin University of China.
Right, and we all know LLMs can generate brilliant text, right? But the Wang paper highlights a major bottleneck. Text generation fundamentally is just a passive process.
It's reactive, yeah.
So the mission for this deep dive is to demystify how developers are moving these models from passive text predictors to active, goal-oriented participants within dynamic environments.
We're basically shifting from querying an oracle to deploying an autonomous worker.
Okay, let's unpack this. To really get started, we need to establish the baseline parameters.
Yeah.
How are we defining an autonomous agent in this specific architectural context?
Well, the researchers actually anchor their modern framework to a classic definition. It's from 1997 by Franklin and Gracer.
Oh, wow, that goes back a bit.
Yeah, and they defined autonomous agent as a system situated within an environment that actively senses that environment and acts on it over time in pursuit of its own specific agenda.
And for decades, achieving that was incredibly difficult.
Oh, nearly impossible. Past AI agents, particularly those built on pure reinforcement learning, were trained in highly isolated, constrained environments.
Wow.
They were essentially optimizing a scalar reward function based on really rigid heuristic rules, which just made them incredibly brittle. If you change the environment even slightly,
The model's performance would just collapse.
exactly, because it lacked generalized world knowledge.
And that is where the introduction of the large language model changes the equation entirely. By using an LLM as the central controller, like the cognitive engine, the agent inherently possesses the vast web knowledge it was pre-trained on.
Right, it brings context to the table.
Yeah, and the paper features this striking chart-tracking publication volume in this specific domain. From 2021 through 2023, the trajectory goes completely vertical.
It's an explosion.
Totally. You see major architectural milestones dropping in rapid succession. WebGPT emerges in late 2021, setting the stage for autonomous web navigation. And that is followed closely by projects like AutoGPT and Voyager in early 2023, which demonstrated sustained multi-step execution in complex spaces.
I like to think about it this way.
Go for it.
If a standard LLM is a powerful brain in a jar, an autonomous agent is giving that brain a body, a notebook, and a to-do list so it can actually walk around and get things done.
That is the perfect analogy.
What's fascinating here is that utilizing LLMs as core controllers introduces a natural language interface to the agent's internal operations.
Okay, wait. What does that mean in practice?
So unlike older reinforcement learning models where the decision-making process was buried in opaque mathematical weights and gradient descents.
Like a black box.
Exactly. LLM-based agents process variables, formulate plans, and execute commands using semantic human language.
Oh, wow.
This provides an unprecedented level of interpretability. Developers can literally read the agent's internal prompt chain to debug its reasoning process. They can see exactly why it selected a specific action over another.
Because it's literally talking to itself in English or whatever language.
Yeah, precisely.
Moving into the actual construction of these systems, the Wang paper proposes a unified four-part framework for agent architecture. They break it down into profiling, memory, planning, and action modules.
The hardware, essentially.
Right. Starting with profiling, this is the process of establishing the agent's core identity and behavioral parameters. You are essentially defining the initial state of the agent by assigning it a persona.
Which is almost like rolling a character in a role-playing game.
Totally. You give them an age, a gender, an occupation, psychological traits, and even social relationship matrices.
The profiling module is the anchor that dictates the agent's subsequent behavior across all the other modules. And the survey outlines 3 primary methodologies for generating these profiles.
Let's hear them.
The most straightforward is handcrafting. A developer manually structures the system prompt to define the persona.
Which is great for one bot, but
It fails to scale, yeah. While this allows for hyper-specific control over a single agent, if you are attempting to build a multi-agent simulation, simulating an entire supply chain or a small city,
manually tuning hundreds of distinct profiles becomes a nightmare.
computationally and practically inefficient. So to solve that scaling issue, developers turn to the second method, which is LLM generation.
So the AI builds the AI.
Basically, instead of hard-coding every profile, you engineer a few foundational seed profiles that establish the basic rules and demographics of your simulation.
The paper highlights a project called Reagent for this, right?
Yes, Reagent was designed to simulate user behavior in recommender systems. So the researchers crafted a small batch of baseline profiles containing age brackets, cinematic preferences, basic psychological traits.
Right.
And then they deployed a secondary LLM to procedurally generate thousands of unique, fully fleshed out agent personas based on those initial seeds. It populated the entire simulation automatically.
That's incredibly efficient. But what if you need real-world accuracy?
That brings us to the third and arguably most rigorous profiling method, which is dataset alignment.
Okay.
In scenarios where the simulation must accurately model reality, generating random personas is insufficient. Dataset alignment ingests real-world demographic datasets.
Like census data?
Census data, economic surveys, psychometric evaluations. It translates those statistical parameters into natural language prompts.
Ensuring the agent population accurately mirrors the specific human population you're studying.
Exactly. It anchors the simulation's outputs in empirical data.
So once that baseline identity is established, the agent obviously requires a mechanism to retain and retrieve information over time. Much like us, without memory, an agent traversing an environment would suffer from persistent amnesia.
It wouldn't be able to compound its learning.
Right. So the paper models agent memory on human cognitive science, dividing it into unified memory and hybrid memory structures.
Right, so unified memory functions as a short-term buffer. The agent's immediate observations and recent actions are appended directly to its prompt, residing within the LLM's active context window.
But the limitation there is pretty obvious.
Yep.
Modern language models have hard constraints on their context windows.
They simply cannot hold an infinitely expanding log of every action an agent has ever taken.
Exactly.
Yeah.
So hybrid memory architecture bypasses this token limit by combining that short-term buffer with an external long-term storage system.
Typically a high-dimensional vector database.
Right. When the agent experiences an event, the text log is converted into a mathematical vector embedding and stored.
Because context windows are limited, when the agent encounters a novel situation, it isn't reading a massive text file of its entire history.
It takes the current situation, vectorizes it, and performs a cosine similarity search across the database to retrieve the memories that map closest to the current geometry.
And the survey emphasizes 3 specific criteria the system uses to filter this retrieval: recency, relevance, and importance.
Break those down for us.
Sure. Recency biases toward newer events. Relevance evaluates the mathematical proximity of the embedded vectors.
How similar the situation is.
Exactly. And importance is a separate score calculated by the LLM to rate how fundamental a specific memory is to the agent's core profiling parameters.
This gets really cool. The sophistication of this system is best demonstrated by a process called memory reflection.
Oh, the Klaus-Mueller example.
Yes. The survey details an agent named Klaus Mueller to illustrate this. An agent's database might be cluttered with hundreds of low-level observational logs.
Like Klaus read a textbook on quantum mechanics.
Klaus scheduled a meeting with the head librarian.
Klaus drafted a hypothesis on a whiteboard.
Right, all this granular stuff. During memory reflection, the system periodically pauses, retrieves clusters of these low-level logs, and prompts the LLM to synthesize them.
The model extracts a high-level abstraction, outputting a completely new memory. Something like, Klaus is highly dedicated to academic research.
And that abstracted trait is then vectorized and stored. It allows the agent to operate on high-level conceptual summaries rather than drowning in raw data logs.
That abstraction of experience is what enables the third architectural pillar, which is planning.
Memory synthesizes the past, but planning is required to navigate the future.
Exactly. Complex, multi-step goals cannot be solved with a single inference pass. The agent must deconstruct high-level objectives into executable subtasks.
And the survey categorizes planning mechanisms into two paradigms. The first is planning without feedback.
Which relies entirely on the model's internal reasoning capabilities. Techniques like chain of thought prompting force the model to output a single, step-by-step logical sequence before acting.
And Tree of Thoughts expands on this, right? Allowing the model to generate multiple diverging reasoning paths, evaluating each branch simultaneously before committing to the optimal route.
If we connect this to the bigger picture, planning without feedback assumes a static, perfectly predictable environment.
Which real environments rarely are.
Right. The moment an agent takes its first action, the environment state usually shifts, rendering the pre-computed plan obsolete.
So they need the second paradigm.
Planning with feedback. Here, the agent operates in an iterative loop. It plans, acts, observes the outcome, and dynamically adapts.
That feedback can be environmental, like a compiler throwing a syntax error when the agent writes bad code.
Or it can be human in the loop, where the agent pauses execution to request clarification from the user.
Or even internal critic modules, where a secondary instance of the LLM evaluates the primary agent's output against the original objective before allowing the action to proceed.
And the culmination of profiling, memory, and planning is the final architectural pillar: action.
This module defines the agent's interaction space, and we are seeing a massive expansion beyond simple text outputs. Agents are actually doing things now.
They're being equipped with specific tool use capabilities. The survey points to architectures like Hugging GPT, which operates as a central node capable of parsing a complex user request, identifying the necessary subtasks, and autonomously triggering specific, specialized AI models from the Hugging Face ecosystem to complete them.
Another powerful example is Viper GPT, which solves complex visual queries not by guessing, but by autonomously writing and executing Python scripts to interrogate the image data directly.
But establishing that four-part architecture, the hardware, is really only half the challenge. The survey then transitions to the software.
The methodologies used to endow these agents with specialized capabilities.
Exactly, how they learn. The literature divides this capability acquisition into two overarching strategies: with fine-tuning and without fine-tuning.
Let's start with fine-tuning.
The fine-tuning approach represents traditional machine learning. It permanently alters the model's underlying neural weights by training it on highly specific, domain-relevant datasets.
The paper illustrates this with a project called WebShop. Researchers built a fully functional simulated e-commerce environment populated with over 1 million distinct products.
Huge dataset.
Massive. They recorded human operators navigating the site, capturing every search query, click, and purchase decision as a state action pair. By fine-tuning the model on these human trajectories, the agent learns the underlying probability distribution of successful navigation strategies.
And developers can also fine-tune using synthetically generated datasets, leveraging a more massive LLM like GPT-4 to generate millions of edge case scenarios to train a smaller, more efficient agent model.
But fine-tuning requires significant computational overhead and direct access to model weights, which isn't always feasible.
No, it's expensive. That's where mechanism engineering comes in. This circumvents fine-tuning by designing environmental architectures that force the agent to learn dynamically without altering its base parameters.
Here's where it gets really interesting. How do they do that?
Trial and error is a primary mechanism here. An agent executes a task, and a deterministic critic module evaluates the state change. If the task fails, the critic generates a natural language explanation of the failure mode.
Like telling it exactly what went wrong.
Exactly. The agent incorporates this critique into its short-term memory buffer and attempts the task again, adjusting its parameters based purely on prompt-level feedback.
And researchers are also deploying crowdsourcing mechanisms among multiple agents to synthesize capabilities. Instead of relying on a single agent's reasoning, you spin up a multi-agent environment where different personas tackle the same objective.
They present their solutions, critique one another's logic, and engage in an iterative debate.
It's incredible. Through this structured conversational protocol, the collective swarm mathematically and logically converges on a consensus solution that typically outperforms the capability of any individual agent in the network.
The most robust form of mechanism engineering detailed in the paper, though, is experience accumulation.
Oh, Voyager.
Yes, beautifully demonstrated by the Voyager project. Researchers deployed an LLM agent into the game Minecraft with absolutely zero pre-programmed knowledge of the game's mechanics or recipes.
Let's just drop in blind.
Completely blind. The agent was tasked with exploring the world. To interact, the LLM had to write executable JavaScript code. Initially, its code would fail.
Naturally.
The Minecraft environment would return a stack trace error. Voyager would read that error, diagnose the logic flaw, rewrite the function, and execute again.
The critical breakthrough with Voyager is what happens upon success. Once the agent successfully coded a sequence to, say, mine a block of iron or craft a sword, it didn't just move on.
Oh, it kept it.
It vectorized that successful code block and saved it to an external persistent JSON skill library. As it continued to explore, it accumulated this vast retrievable database of complex executables.
It basically bootstrapped itself from a blank slate into a highly capable expert entirely autonomously by leveraging its memory and planning modules to refine its action space.
The implications of these architectures extend far beyond gaming and theoretical benchmarks. Let's talk about why you, listening to this, should actually care.
Because it's moving into the real world. The Wang survey maps out how this technology is currently migrating into high-stakes applications.
For instance, in the realm of social science, researchers are utilizing these architectures for complex social simulation. Traditionally, testing macroeconomic policies or sociological interventions required years of observation or expensive, ethically complex human trials.
Right, but projects like generative agents or social simulacra allow researchers to construct virtual communities populated by dataset-aligned LLM agents.
So they can introduce a new variable, like a moderation policy on a social network, and observe the cascading effects through the simulated population.
Though the researchers do highlight a significant statistical artifact to watch out for in these simulations, it's termed hyperaccuracy distortion.
Hyperaccuracy distortion, meaning what?
Because LLMs are fundamentally optimized to predict the most highly probable, logically coherent text, they often simulate human behavior with a level of rationality that doesn't exist in reality.
Because real people are messy.
Exactly. The agents might resolve conflicts too efficiently or follow economic incentives too perfectly. They fail to account for the irrational noise, emotional fatigue, and general unpredictability inherent in actual human populations.
So calibration requires injecting intentional noise back into the agent prompts to maintain ecological validity.
Precisely. Transitioning to the natural sciences, the shift is equally profound. Consider ChemCrow, an agent architecture designed to operate as an autonomous research chemist.
That sounds slightly terrifying, but amazing.
It's brilliant. The LLM is integrated via APIs to 17 specialized computational chemistry tools and external databases. A user provides a high-level objective, such as the synthesis of a novel insect repellent.
And ChemCrow autonomously maps out the required reaction pathways. It queries the external databases to verify chemical properties, plans the procedural steps, and crucially, runs continuous automated hazard checks.
Right, to ensure it doesn't accidentally synthesize a toxic or explosive byproduct during the execution phase.
Safety first. What I find truly fascinating about the engineering and software applications is how they force us to rethink traditional organizational structures. The paper details a framework called ChatDev, which operates as an entire virtual software development company.
ChatDev is wild. The user inputs a single natural language prompt describing the desired software. The system then spins up a cascade of specialized agents. An AI CEO, an AI product manager, a chief architecture officer, an AI coder, and an AI tester.
And the architecture of ChatDev relies entirely on the multi-agent conversational protocols we discussed earlier. The CEO agent delegates the high-level requirements to the architect, who designs the system structure.
Which is then passed to the coder agent, who generates the raw Python scripts.
And then the codebase is seamlessly handed to the tester agent, who runs it, identifies bugs, and literally opens a natural language dialogue with the coder to demand revisions.
This multi-agent loop iterates until a fully functional, executable software package is compiled. It fundamentally changes the bottleneck of a software development from human coding labor to high-level system prompting.
We are also seeing the action module break out of the digital sphere and into physical environments through embodied AI and robotics.
Right, the survey points to systems like TidyBot. Instead of relying on hard-coded kinematics to clean a room, TidyBot leverages a language model to translate natural language user preferences into physical robotic actions.
It processes text inputs regarding how a specific user likes their laundry sorted or their desk arranged, mapping those semantic instructions to his physical manipulator arms.
Allowing for generalized robotic hardware to adapt to hyper-personalized dynamic home environments.
So what does this all mean? We have traced the architecture from the foundational profiling of an agent, through its high-dimensional memory and adaptive planning loops, all the way to its real-world integration in laboratories and software development. When parsing the entirety of this comprehensive 2025 survey, how do we encapsulate this structural shift?
The synthesis of all these developments points to a fundamental recalibration of human-computer interaction. For the entirety of computing history, software has functioned as a reactive tool.
It waits in a dormant state for a human operator to input a specific command.
It executes that single command and returns to a dormant state. But the integration of LLM controllers into the agent architectures outlined by the Renmin University team transitions software into a proactive collaborator.
These systems actively monitor their environment, query their persistent memory states to contextualize new data, adapt their operational plans in real time, and execute complex tool chains to achieve abstract objectives.
With minimal human oversight.
The bottleneck is no longer the machine's ability to process information. It is our ability to design the frameworks, the profiling, the hybrid memory structures, the mechanism engineering that direct this massive cognitive capacity toward useful outcomes.
We are building digital entities that can abstract experience, debate logic, and accumulate skills autonomously.
Which is both incredibly exciting and undeniably profound.
This raises an important question. As these autonomous architectures become deeply embedded in both our professional workflows and our domestic environments, the operational distinction between a piece of software and an autonomous representative is going to effectively disappear.
Which leads me to a final specific thought I want to leave you with today. We explored dataset alignment and how developers can engineer an agent to perfectly reflect a specific demographic profile.
We unpacked how hybrid memory allows these systems to continuously vectorize and retrieve context.
And how memory reflection enables them to abstract deep behavioral traits from superficial daily logs. Now, project that architecture onto yourself.
A digital proxy.
Exactly. What happens when you train one of these autonomous agents exclusively on your own personal data footprint? Feed it a decade of your emails, your private text messages, your browsing history, your financial transactions, and your calendar events.
It learns you perfectly.
When an agent possesses your specific vectorized memories, your exact behavioral preferences, and your unique patterns of reflection, at what point does it cease to be your digital assistant and fundamentally become your digital proxy in the real world?
That is a staggering thought.
How comfortable are you with a perfectly aligned digital clone, autonomously making moral, social, or creative decisions on your behalf, executing API calls, and interacting with the world while you sleep? It is a structural reality we have to confront as this technology moves from academic surveys into the wild. Thank you for taking this deep dive with us. We will catch you next time.